So we've got y equals x cubed, y equals 8, and x equals 0. The x equals 0 is the axis of revolution. Okay, so we want the region that's bound by y equals x cubed and y equals 8 revolving around the x-axis, or revolving around the y-axis. Okay, so x equals 0. So if we give this a shot, y equals x cubed. Let's just make that in blue. It's going to look, something like that. Y equals 8. Be somewhere up in here. Okay. So we'll pretend that's y equals 8, and then we're revolving around that axis. Okay. No, keep drawing the wrong thing. That axis. It just didn't show up on the instructions, but it was this one, right? And if it wasn't that one, intentionally, we'll pretend it was. Okay. All right. So the first question is: do we do this method thing, or do we do cylindrical shells thing? Okay. And does it really matter which? So I don't know. Maybe the best thing to do is just initially just kind of set up the integrals and then decide which one you think is going to be easier. Okay. So with the disk method, we always want the rectangle to be what in relation to the axis of rotation? We want it to be perpendicular. Okay, so if our initial setup, we think about the disk method, then we want our rectangle to be here, so it's perpendicular to the axis of rotation. Okay, so the little side of that rectangle, that then would be dy, because that little side is vertical. So that tells me I'm integrating with respect to y. And with the disk method, remember, everything hinges on the volume being pi r squared times h. Right? Because we're looking at a little full cylinder there. Okay. So the radius is the height of the disk, right? Or the height of the rectangle. So what would my radius be in this case? So we've got to go from here to here. So the radius is whatever the x coordinate is. Because you're going from 0 to whatever that function is. All right, so we want the radius then is whatever that x coordinate is. But we're integrating with respect to y. So we need the x coordinate in terms of y. So we look at our function, say, okay, well, then for my radius, we're going to have x equals what the cubed root of y. Yep. So that's going to be my integral, and then we've got to decide what the bounds are. So what's the lower bound? So remember, we're going this way, right? Integrating with respect to y. So the lowest spot in that little region that's all nice and enclosed, what is the y coordinate for that? Yeah, it should be 0 because we're talking about going from here up. Okay? So the y coordinate, the lowest y coordinate is 0. The highest y coordinate is 8. So we're going to go from 0 to 8. Well, that actually wouldn't be too bad of an integral to do, right? So let's just go ahead and do that, and then we'll set up the cylindrical shells just to have a good comparison. So that would be, I'm going to write that as y to the 2/3. Let's see, we'll add 1 to the exponent, and that's going to give us 5/3. We'll divide by that new exponent, so we got a 3/5 there. And why did I write my integral sign if I'm going to go ahead and do the antiderivative? I don't know. And we'll evaluate that from 0 to 8. So at 8, we're going to have 3/5 times 2 to the 5th minus then the 0. 2, 4, 8, 16, 32. So 32 times 3 would be 96. So we get something like 96 pi over 5. Okay, so that would be it with the disk method. Now, just now out of curiosity, so we can do a good, honest comparison between the two. Okay? How do we set this thing up with the shell method? So the cylindrical shells, let me redraw my little figures here. With the cylindrical shells, then we set up our rectangle parallel to the axis of rotation. So it's going to go from here to here. So that's going to be the rectangle that we rotate around to make our little cylinder thing. So that means the narrow side of that is a dx. So we're going to integrate with respect to x. And remember, that's based off of the volume being this rectangular prism type thing. So this is the dx. The height of the prism is, well, whatever the height is, okay? But the radius, or down here, the radius is the circumference. The length of that is the circumference of the circle. All right, so the circumference of the circle then, let's just go ahead and deal with that. When we rotate that around, this is going to be the radius. The little spot from the x-axis over to our rectangle. Because that's kind of the base, right? When you spin it around, think about that, that's the base of the cylinder. Okay. So what is that radius going to be? So you go from 0 out to the rectangle, just going straight out. So, well, it's going to be the x coordinate. Okay. Oh, no, it's just going to be x. Right? Because all we got to do is we got to go out from here to here. That's the radius. So it's just simply the x coordinate. And we want it in terms of x, so we get to leave it alone. So the last one, with this method, we had to have it in terms of y. That's why we had to solve it for y to get x equals whatever it was. Okay? Here, it's just the x coordinate is the radius. So our volume, we're going to have 2 pi x. Now we need to think about the height. Okay? The height of that rectangle is determined by what? Yeah, because it goes from up here, and the bottom of the rectangle is wherever it hits that graph. Okay. So it's the 8 and the y coordinate, right, of the graph. This is how high up that graph is. So think of everything in terms of just the x and the y coordinate. Everything is based off of how far left you go or how far up and down. So you can always think about it in just simply in terms of the x and the y coordinates. And you can start by writing it that way if you want. Say, well, you know what? I know this is going to be x minus whatever that y coordinate is. Okay? But I know we're supposed to be in terms of x, because that's the width of that rectangle. That's the delta x. So if I have a y in my equation, I need to go back and substitute in. So, okay, well, what was y in terms of x? Well, y was x cubed, wasn't it? So instead of the y, we'll stick an x cubed there. And then we'll have, yeah. And then we'll go from 0 to what? Yeah, we'll go from 0 to 2, okay? Because the x coordinate, right? How far over do we go? So the question is, up here, what is that point? It's where x cubed intersects 8. All right? So to find that point, you say, okay, well, x cubed has to equal 8, which means that x would equal 2. We'll go from 0 to 2. So the volume equals that. I'm going to factor out that 2 pi just because. Now I can just distribute that just to x to the 4th. This one's not going to be a bad integral either. So that's going to be 4x squared minus 1/5 x to the 5th. And we'll evaluate that from 0 to 2. So at 2, let's see, we'll get 4, that's 16 minus 32 over 5, 32 over 5, and then minus 0, since both of those have a x in there. Okay, so we'll have minus 0. Let's see, 16, 5, 30, 80. So 80 minus 32, 8, 28. And now the question is, what did I do? We got 2 times 28 would only be 456. So let's see, 0. What now? You know, I swear to God, I looked down at my 32 and thought that was a 5. Don't forget your bonus point. Oh, look, that turned out just perfect then. So if you learn how to subtract, it helps. Okay? Or how to read your own writing, it helps, right? So I mean, here's the nice thing about this example. It really didn't make a big difference which method we use. Okay? Sometimes it doesn't. Okay? Now, if I were working this on homework and I tried this method, I'd be like, oh, yep, I'm not going to try the other method, right? I'm just doing it here so we can kind of compare the two and see this method slightly easier, okay, but not by much. The moral of the story is, for the most part, it doesn't matter which method you use. There are some distinct cases where one's better than another, okay? There's a lot of cases where that's not the case. Okay? So whichever one you're most comfortable with is the one I would start with by default. I wouldn't sit there and look at a picture, look at the equations, and try to figure out, well, which one's best. I would just start with whichever method I like best, whichever one makes sense setting it up. Then if it turns out to be kind of complicated, I would switch to the other method. Okay? That's kind of my default problem solving for this. Pick one, stick with it. And in the case that you look at the integral and go, I don't know how to do that integral, or it's going to take me a while, sketch out the other one. Okay? See if it'll be any better. No, not necessarily. But that might be by default the way that you want to start the problem. Okay? So yeah, I mean, certainly if you're comfortable with both methods and it doesn't matter to you which one you set up first, then maybe that's a good way to choose what you want to do. Say, well, I've already got everything in terms of X. Let's pick the one that has me integrating with respect to X. Then I don't have to worry about solving equations and screwing up that step. Okay? So sometimes to me, the fewer steps there are and the fewer chances you get to do a 80 minus 32 being 28. Okay? So, but we okay with this one? So we want the region enclosed by these two graphs. Okay? And we're going to rotate that about the x-axis. Okay? So let's see, 1/4 x squared. Now that's a parabola facing upward. Then we have the 5 minus x squared. That one's a parabola facing downward. We're going to rotate about the x-axis, and it's the region enclosed by those things, so it's just this spot in here that we're rotating around. All right, so this one we can think about just a little bit and maybe come up with a plan of why we would choose one over the other. Okay? If I choose to use the disk method, okay, then my disk is going to run, my rectangle is going to run here, perpendicular to the axis of rotation. Now, advantages of that would be the height of that disk is pretty easy because it's always bound. One function is always on top, the other one's always on bottom. Okay? But we do have to be a little bit careful because we have this space that's underneath that we have to subtract out, right? So we would have two integrals to deal with, but they're pretty straightforward integrals. We're only integrating a parabola in each case. That's a pretty easy antiderivative to do, okay? And we just got to do some subtraction. Okay? So the cons of it is we have to do two integrals because we've got to subtract out that bottom piece. Okay? Now, if we did the shell method, then our rectangle would go this way, all right? And then we would have to rotate that sucker around. Now, a distinct disadvantage to that would be on this upper part. Okay, that rectangle would run between the same function, the 5 minus x squared. And then on the lower half of it, the height of that rectangle would be between the same function there. And so we need to know how to deal with that. Now, is there any trick we can use to maybe simplify our calculations either way? Yes, and that's one thing I would definitely think about doing is that these parabolas are symmetric, even though I don't have it drawn that way. Okay, you know, I'm not an artist. Okay, it is symmetric, so we could limit ourselves, and instead of going all the way across, we could go just from the y-axis over in this case, or in the disk case, we could integrate from 0 to whatever. Start having a bound at 0 is nice because that makes the calculation later really super easy typically, right? Okay. So either way, we can simplify the calculations by changing the bounds, but what are we going to have to do with our volume at the end? We're going to have to double it because we're only doing half of this shape. So you've got to remember, if you use symmetry and stuff, that's great. Just remember whether you have to double it or quadruple it or triple it or whatever it is, depending on the shape. Okay. So with that being said, the shells method then is always going to go from 0 to one of the functions. Okay. That makes things a little bit easier. But we would still wind up with two integrals, wouldn't we? Because we'd have the top half, then we would have the bottom half of it. Okay. Because that rectangle ends at the 5 minus x squared for the top half. And then the rectangle ends, it goes from 0 to the 1/4 x squared for the bottom half. So does anybody have a one they want to use? Sure. Okay. So let's do disk method. Okay. So remember, for the disk, the volume of a disk is pi squared times h. In this case, h is just the dx, right? Okay. So we're going to have the integral pi, and whatever the radius is, squared. And let's see, that was the dx. Now, on this one, so that's my red rectangle in here. You have to start off with the top one, and then we'll subtract out the bottom, right? Okay. So that top function is the radius. If we just go from 0 up to the y-coordinate, okay, that would be the radius for the outer part of it. Remember, this is going to be one of those washers, the little hollow disc. Okay, and that is the 5 minus x squared. And then we're going to run those rectangles all the way over till they intersect, right? So we're going to start at 0 because we're going to use our symmetry. Now, where do those two things intersect? So we have 1/4 x squared has to equal 5 minus x squared. So add x squared to both sides. That's going to be 5/4 x squared has to equal 5. And then we'll multiply by that. So x squared is, stop that, go away. I don't need no sticky note. So x squared is going to equal 4. That gives me the positive or negative 2. Which is great because I know this one's going to be the positive 2, right? So we're going to go from 0 to 2. Now for the cylindrical shell method, Remember, the volume that we're looking for is 2 pi r h. And then let's be a little bit careful. The width of my little box, when we unroll it, right, that would be the dx. Okay. So remember, in this case, that's the dx of the dy. The volume for that prism is, in this case, the dx of the dy. All right, so that's going to give me the integral of 2 pi. Now the radius goes from 0 to the 5 minus x squared on the top. Okay, because remember we have to do a top half and a bottom half. Okay. So we're splitting it up. I say the top half and the bottom half is one of the rectangles we have to do is for this half of it, because any rectangle we put there is going to go from the axis to the 5 minus x squared, right? And anything below that will go to the 1/4 x squared is where it'll end. Okay. So the radius then will be 5 minus x squared. Well, that's the height of the rectangle. The radius is still the y coordinate because we have to get from here up. Okay, so the y coordinate in terms of x, because we're integrating with we're integrating with respect to y, aren't we? Okay. That'd be a dy plus, and then we'll go back and fix things. Okay, it's time to take these little steps. Now on the bottom half, we'll have the 2 pi, and that was 1/4 x squared times the y coordinate for the radius of that cylinder. Now since it's dy, we want everything in terms of y. Give myself a little more room here. Now, in terms of y then, if y equals 5 minus x squared, then we'll have x squared equals 5 minus y. We'll have to take the square root. That's a minus y. So that'd be the square root of 5 minus y. Now, what would be the bounds for that integral? The bounds, we just want the top half, right? So what are the y coordinates for the top half? Again, we go look at this intersection point. You know this intersection point was something, well, was 2 something. Okay, and so 1/2 or 1/4 x squared, that would be at 1. So we would go from 1 all the way up to 5 because that's the top part of that parabola. That makes sense? Now my other integral then is going to go from 0 to 1 because it's got to start at the bottom and go up to that break point. Okay. And then we'll have the 2 pi. Now instead of 1/4 x squared, that'll be equal to y. So multiply both sides by 4. And then we take the square root. That'll mean x is 2 square root of y. Times the y and the dy. Okay. I do not know about you, but this method looks a whole lot better than having to deal with all of those square roots and stuff. Okay? Yeah, we're still going to have to subtract the lower one. Right, I mean, but the integration is, right, so we have to go 0 to 2. I didn't write that down. Pi, and that's 1/4 x squared dx. But those integrals, that this method look substantially easier to do. So that's what I would stick with. Okay. Okay. Well, we can do that. In fact, just to make my writing a little easier and stuff, I'm going to go ahead and factor a pi out of all of that. Okay. And then we've got 5 minus x. In the integrals are the same. Factor the pi out. We're just going to wind up with that. All right. All right, so just simplifying things, just so that way it's a little easier on the integration part. Let's see, that's going to be what, 25x minus 10 thirds x cubed plus 5 3/16 x to the 5th. And we'll evaluate that from 0 to 2. So 50 minus 80 over 3 plus 3296 over 16. And minus 0. I'm just not going to bother writing the minus 0. Let's see, 96 and 16, that'll divide into that. Well, 6 times? Yeah, so that's 6. So that's 18 over 3. These are my common denominators and stuff. So let's see, 70. Maybe 88 over 3. So 88 pi over 3. I don't know why I wrote down 80. Hold on. So that's 4. That should be 40. Wait, you're talking about where? Well, let's see, because wasn't 96 over 16 equal to 6? All right, so that's 6 over 1. All right. But, hold on, I screwed up this fraction. I don't know where the 80 came from. Oh, just because, no, never mind. I know what I'm doing. We evaluated that's going to be 8 times 10, yeah, so that was 80, yeah. I was thinking in the wrong step, so that's 80 over 3. So maybe 88 pi over 3. You okay with that? So definitely a good example where this method is far better than the other one, because trying to do that, you're going to definitely wind up doing integration by parts. That's going to add in some stuff that's complicated that you don't necessarily have to do, right? There may be cases where you have to do integration by parts. This just isn't one if we pick a different method. Yes, because we did our symmetry stuff. So the volume is 2 times that. 88.5/3. So that would definitely 196. 176, yeah. Well. Now, on the exam, I'm going to ask you to set up one using this method. If you set it up the other way, it's not going to get you anywhere. I'll ask you to set up the question using the symmetrical shells. Okay? Any of that you actually have to evaluate, you'll have your choice. Okay? If I don't explicitly state use this method, just in general on any test, then you don't have to use even what we've done in class. Okay? As long as it's a valid method, I don't care how you do some of these problems. Right? If we have multiple ways of doing things like this, and I don't specify, then I'm not worried about which method you pick. Okay? Also pay attention, because if it's just set up, no, then you would get to stop back here once you've got the integral and all the right variables. You don't have to evaluate it. Okay? So pay attention to the instructions too, because I've seen some people waste a lot of time not reading the instructions and then trying to evaluate really ugly integrals when all I wanted was just what is the integral. Okay? But we have questions about this one? Well, that's kind of small. So that's an x squared, just in case you can't read it all. X squared, scoot down a little bit so that way it doesn't get in the way. Y equals 2 minus x squared, but this time our axis of rotation is x equals 1. All right, so just picture-wise, where do those 2 points intersect, or those 2 graphs intersect? So when is x squared equal to 2 minus x squared? So that's going to be when x is a plus or minus 1. All right. So my axis of rotation is here at x equals 1, and then I'm taking that whole little eyeball shape and spinning it around that. So right off the top of my head then, again, your disk method, that would be the cylindrical shells method if I set my rectangle up that way. Now, the reason I'm thinking about this one first is because the height is clearly between those 2 functions. Okay? So it'd be easy to do this minus this to get the height of it. Okay? and I don't have to worry about breaking it up into different regions and stuff like that. So it might be an easier setup than the disk method, because the disk method, again, if I set my rectangle up going sideways, here I'm going to have a top half and a bottom half. All right. Then I'm going to have to worry about on the top half, my rectangle goes between the function and itself. Okay. I can't use the symmetry because I'm not rotating about the middle of it. So the volume of the inside piece is going to be different than if I tried to do the volume of the outside piece. So I couldn't just double it type thing. So I can't use the symmetry. So I'm thinking the cylindrical shells might be better in this case. Okay. Now, do I know that for a fact? No. Just my best guess. Okay. So that's what I'm going to start off with this. So I'm going to use the cylindrical cells. Okay, well, again, 2 pi r h, and then of course the width. Remember, the width is the dx. Okay. So the two things I need to know are the height and the radius, right? So what's the height? The height goes between the top function and the bottom one. Okay. Now we want these in terms of x, okay? Because our little bottom here is the delta x. Okay. So remember that it's the narrow side that always tells you what variable you need to integrate with respect to. So the height will be the 2 minus x squared minus the bottom function. So I'm going to go ahead and simplify that. Just combine my like terms, nice and simple. What is the radius that I'm looking for? No. No, but closer. 1 minus x, okay? We're going from here over to this spot, right? That spot is x units away from the origin, right? But that's not our radius. The radius is the other side of that, which would be the 1 minus x on this side. Okay? So that would be the distance from here to the axis of rotation. And that's where you got to be careful of when you're thinking about the radius and stuff. It's always the axis of rotation to the rectangle. That makes sense? That might be the number one place that people make mistakes setting these things up, especially when it's not rotating around the x or the y axis. Okay? So that's the one spot where I tend to be really extra careful, just because it's so easy to mess up. Okay? But it'll always be axis of rotation minus x. Or if it's with respect to y, it's going to be axis of rotation minus y. And then you just have to make sure that you're using the right variable. So if I were integrating with respect to y, maybe I'd have to change the x's to y's, blah, blah, blah. Okay? So the radius then is going to be the 1 minus x. And then what are my bounds for my integral? So since it's with respect to x, and I'm looking at this whole region in here, I got to go from the far left of it to the far right. Yep. So remember, our x-coordinate over here was 1. This x-coordinate was a -1 when we solved it earlier. Those were the intersection points. So we're going to go from -1 to 1. Now, just simplifying things before I worry about derivatives, before I worry about integrals. Always simplify stuff first if you can. It just tends to make the integration easier. I went ahead and factored out a 2 out of that second factor and brought it outside of the integral sign. That's why there's the 4 pi there. So you're going from -1 to 1. Just looking at what kind of cancels out and what doesn't and type stuff, all right? So that's going to be 1 minus a third plus 1 minus a third. So 2 minus 2/3. So that'd be 6, 4, 6. So that'd be, all right, let's see, hold on. 6, yeah. Okay, that should be 1 and why did I write 4, 6? I'm like that. I know that's not right. It's 4/3. So 16 pi over 3. So if you write down all of the little steps and stuff, it is kind of easy. They're kind of long problems, right? But it's one of those cases where at least here the individual steps aren't so bad. You good with this? So yeah, I think definitely if you tried to set up the disk method, just thinking about the setup, okay? So we just want the pi r squared for our volume, right? This is really pi r squared h, but remember the h is just the dx or the dy or whatever we're doing. So in this case, it would be dy. Now how, let's just kind of focus on the top one. How do you get the height or the radius for that? So you just want to be slightly careful because remember there's this empty space down below. So we want to go from 1 all the way over to the edge, the far edge of the 2 minus x squared. But we need it in terms of y, right? Because we want to dy. Because our little rectangle, the small part of it is going up and down. When you solve this for y, because right now we have y equals 2 minus x squared. Okay? So when I solve that for y, we'll have x squared equals 2 minus y. So x is the positive or negative square root of 2 minus y. So I have a choice. Do I want the positive or do I want the negative? Are the x coordinates positive or negative over here? So then I want the negative. When I do stuff on this side, I want the positive because the x coordinates are positive. Okay? So we're just going to have to set up then the one integral, and we'll go from, what are the y coordinates here? So I know the x coordinate was 1, and y equals 2 minus x squared. So 2 minus 1 would be 1 as well. So we're going to go from 1 to 2, because the top of that parabola is at 2. Okay? That's the whole height that I need to go in between there. Then we'll have pi. The radius is 1 minus whatever that end point is, which would be the negative square root of 2 minus x squared. It's that squared, right? dy. So that's the top half before we subtract off the other part, right? So then we would have to do a minus 1 to 2 pi times, and that would be 1 minus the positive 2 minus y squared, or 2 square root of 2 minus y. There's no squared there yet. The square's on the outside of all of that. dy. So that would be the top half. And then we would do the bottom half with the other equation, but it would set up, similar to that, right? That seems just a little bit more complicated. So if I started with cylindrical shells, or this method there, and I got to that point, I'd be like, let me just try the other one, okay? Just because it's starting to look kind of ugly.